Okay, let's start today's lecture. The last lecture we were discussing about the counters. Due to some network issue, the lectures were stopped in between. Let's start from the beginning. So far, we have studied about shift registers and the flip flops. Shift registers are used to store or to rotate temporary data in your processor. Now, in today's lecture, we are going to discuss about the counters. Counters are the circuits, logic circuits, which are used to follow or to count a sequence. And when it comes to the definition, counters are sequential circuits which count through a specific state sequence. They can count up like 0, 1, 2, 3, 4, count down or count through other fixed sequences. There are two different types of counters which we are going to discuss today. And the first one is ripple counter or asynchronous counter. In ripple counters, clock is connected to flip-flop clock input at the LSB bit of the flip-flops or the counter. That means only one flip-flop will be connected to the master clock of the system. For all other bits, a flip-flop output is connected to the clock input. That means the output of the first, that is the LSB flip-flop, will act as a clock to the next flip-flop and it will continue throughout the circuit design. Output change is delayed more for each bit towards the MSB and resurgent because of low power consumptions. These are the characteristics of the ripple counters. Now, another type of counter is the synchronous counter or the parallel counter. In synchronous counter, clock is directly connected to the all flip-flops. That means all flip-flop are synchronized with the master clock pulse, or we can say that the clock pulse to the all flip-flop will be same as the master clock pulse of the circuit. Now, for designing the synchronous counter, logic is used to implement the desired state sequence, while the designing of the ripple counter is straightforward, simple, as we are going to discuss in the next coming slides. Now, the benefits are the use of the counters. It can act as simple clock to keep track of time. You may need to record how many times something has happened, how many bits have been received or sent, how many steps have been performed in some computational work. Further, all processors contain a program counter, that is the PC. I think you may have studied in computer first year in computer programming. So program counter all program consists of list of instructions that are to be executed one after each other. The program counter keeps track of the instruction currently being executed and it increments one on each clock cycle and the next program instruction is then executed. So this is the work of the program counter. Further, another benefit of the counter is that it may be used as frequency divider. We'll discuss it with the help of the diagram. Now, the first example of the asynchronous or the ripple counter is 3-bit up counter. So here we are using the up counter. The counter is called asynchronous because not all flip-flops are hooked to the same clock, means every flip-flop has different clock pulse. So here is the state diagram of the counter. You can see that if we start with 0, 0, 0, it will go to 0, 0, 1, that is 1, then 2, 3, 4, 5, 6, 7, and then again 0, and the cycle repeats. So here we use 3-bit ripple counter. As we know, a flip-flop is a single bit storage device. That means the number of bits which we are using to design a counter is equals to the number of flip-flops which we are using. For 3-bit counter, we require 3 flip-flops, and with 3 inputs or the 3 flip-flops, total states will be 2 raised to power 3, that is 8, and which will range from 0 to 7. So we may say when we are using a up counter of 3-bit, it will start from 0 and count up to 7, and after 7 it will again move to 0th state and the cycle repeats. Now when we look into the circuit, you can see we have used 3 flip-flops, T0, T1 and T2. This is your LSB, least significant bit, and the clock of the LSB is 1. Clock of the LSB is equals to master clock. We have used here T flip-flop, and we are utilizing the fact that whenever T equals to 1 and an active clock is given to the flip-flop, then it will change its state. If previous it was 1, then the next state will be 0. That means the toggling effect. So all inputs of the T flip-flops are equals to 1. First clock is the master clock. Output of the first flip-flop T0 is the clock to the next flip-flop T1. Output of T1 is equals to clock of the next flip-flop, and up to in the same manner we can continue our design up to n bit of storage. So how it works, that will be pretty much easier to discuss with the help of the timing diagram. Here this clock is nothing but this is your master clock. So we have used 8 cycles, 8 clock pulses. Let us assume that initially all flip-flops are cleared, means all flip-flops stored value is 0, 0, 0. And you can see in the design that clock first T0, that is the LSB has a master clock as input as T equals to 1. Whenever there is an active clock, the output will change. So let us see how it happens. It is a negative edge triggered flip-flop. Whenever as T equals to 1, whenever a negative edge is detected by the flip-flop, it will change or it will toggle its state. So here initial state is 0. It looks first negative edge, it comes from 0 to 1. Then it will wait again for the negative edge, second negative edge 1 to 0, third negative edge 0 to 1, fourth negative edge 1 to 0, fifth negative edge 0 1, 6 1 से 0, 7 0 से 1, 8 1 से 0. Now it happens, you can directly see for this particular period we are using 2 master clock pulse. So if we take the time period t, then if this is the time period t and the time period of the master clock is 2t, so we can say that the frequency is divided by 2. So again now this Q naught act as clock to the Q1. Sorry, we can say Q naught is clock to the next flip flop and T1 equals to 1. That means whenever there is a negative edge, the output Q1 will change. So it happens here. Now this Q naught will act as a clock and it will detect the negative edge. So initial value is 0 up to negative, first negative edge is detected, output will change 0 to 1. For the next negative edge, it will come from 1 to 0. For the next negative edge, it will go from 0 to 1. And for the next negative edge, it will go from 1 to 0. Now you can see in this particular time period for the Q1, 4 clock cycle master clock are utilized, or we can say that now the frequency is divided by 4. Again we can see this Q1 is clocked to the T2. So what happens now, Q1 will act as a clock as T2 equals to 1. That means whenever there is a negative edge, the output Q0 will change, Q2 will change, and it is happening here. Here we have detected first negative edge, output will change from 0 to 1. For the next negative edge, it will change from 1 to 0. So you can see the sequence output 0 0 0, that is 0, 0 0 1 is 1, 0 1 0 2, 0 1 1 3, 1 0 0 4, 1 0 1 5, 1 1 0 6, 1 1 1 7, and after 7 the value of the output is 0 0 0. That means cycle will repeat, and you can see here it starts with 0 0 0, it will count up to 1 1 1, and again after 1 1 1 the value will be 0 0 0. So it starts from 0, goes up to 7. With every clock 1 is incremented, and after 7 it will again go to 0. So this is how a ripple counter works, and you can directly see the circuit diagram is pretty much easier. For the LSB, clock is master clock. Output of first bit is the clock to the next bit. Output of next bit is the clock to the next state. So this is how a ripple up counters are designed. We can take another example. Suppose here we have used JK flip-flop, and whenever J equals to K equals to 1, then it will act as a T flip-flop, and the circuit diagram is similar as in the case of 3-bit asynchronous counter. Here we have used T flip-flop. Now here I have used JK flip-flop, and J equals to K equals to 1. I have put it for the all flip-flops. This Q0 is nothing but Q0 is your LSB, Q1, Q2, and Q3. Here I have used 4-bit synchronous counter. That means 4 flip-flops are used, and it will count from 0 to 2 raised power 4 minus 1, that is up to 15. So overall states are 2 raised power 4, that is 16. So it will start from 0, go up to 15, then I will come out again to the 0, and the cycle repeats. So here you can see with the clock diagram, master clock, this is your master clock. I have taken here 16 steps. So initial all flip-flop value is 0. Whenever first edge is detected, Q0 is 1. For the negative next negative edge, it will 0. For the next negative edge, it will 1, and it will similarly change its value whenever a negative edge is detected. Now Q0 is clock to the next flip-flop T1, or sorry, J1, K1. So whenever a negative edge detected, the value of Q1 will change from 0, 1, 1 to 0, 0 to 1, 1 to 0. Whenever there is a negative edge, output will change. Now Q1 is the clock to the next flip-flop. So Q1 will act as a clock. I have marked here the negative edges. Whenever there is a negative edge, output will change. Again, Q2 act as a clock to the next flip-flop. Now Q2, here is the first negative edge, and here is the second negative edge, and the Q3 will change whenever it will detect a negative edge, 0, 1, like this. So here you can see it starts from 0, 0, 0, 0, then 0, 0, 0, 1, 1, 0, 0, 1, 0, 2, 0, 0, 1, 1, 3, 0, 1, 0, 0, 4, 0, 1, 0, 1, 5, 0, 1, 1, 0, 6, 0, 1, 1, 1, 7, 1, 0, 0, 0, 8, 1, 0, 0, 1, 9, 1, 0, 1, 0, 10, 1, 0, 1, 1, 11, 1, 1, 0, 0, 12, 1, 1, 0, 1, 13, 1, 1, 1, 0, 14, 1, 1, 1, 1, 15. Then the output automatically changes to 0, 0, 0, 0, that is 0. So it starts with 0 and goes up to 15, and after 15 the next cycle, next state will be 0. Sorry. So this is how our ripple counters are designed. Now after discussing the up counter, let us discuss the down counter. Sorry. In the down counter, the output will start from 1, 1, 1. The output will start from 1, 1, 1, and it will go to 1, 7, 6, 5, 4, 3, 2, 1, 0, and after 0 the value should be 7. So this is the way. Here I have used 3-bit ripple counter. So design is simple. Look at the clock of the second and the third flip-flop. The only difference from up counter is that now the clock is the complementary output of the previous flip-flop. In the up counter, Q0, Q1 acts as a clock. In case of down counter, Q0 bar and Q1 bar will act as a clock. That is the only difference between up counter and a down counter, and it will be pretty much easier when we are we'll see the timing diagram of this counter. And let us discuss the timing diagram. So here we go. Master clock is the input to the first flip-flop. So whenever there is a negative edge, it will change its state. So initial value was 0, 0, 0, 0 for the all flip-flops. So 0, 1, next negative as 0, next negative as 1, next negative as 0, next negative as 1, next negative as 0, then 1, then 0, then 1. This is how happens. Now as we have q naught bar as a clock, so I have designed here q naught bar. Q naught bar will be opposite, that is a complement to the q naught. So I have drawn this q naught bar. Whenever it is 0, it is 1, 1, 0. So it is just opposite to the q naught. Q naught bar will act as a clock pulse. So I have marked the negative edges here. Negative edges are there. Here, these are the negative edges. Now with the when there is a negative edge in the q naught bar, q1 will change. So initially q1 was 0. It detects negative edge, then 1. Next negative edge 0. Next negative edge 1. Next negative edge 0, and next negative edge 1. Again q1 and q1 bar will be complementary. Q1 bar is now the clock pulse. Here we can see from the design, here is q naught bar is clock pulse, here is q1 bar is clock pulse. So I have the q1 bar, I have plotted q1 bar, so it will be complement of the q1, and I have marked the edges, negative edges of the q1 bar. So these are the negative edges of the q1 bar. So these are whenever there is a negative edge, output q naught initial was 0, it will change to 1. Next negative edge, it will change to 0, and next negative edge, it will change to 1. So whenever we look the value of q naught, q1 and q2, where q naught is the LSB and q2 is the MSB, it starts from 0, 0, 0, and it goes to 1, 1, 1, that is 7. Then 1, 1, 0, 6, 1, 0, 1, 5, 1, 0, 0, 4, 0, 1, 1, 3, 0, 1, 0, 2, 0, 0, 1, 1, 0, 0, 0, 0, and next value is 1, 1, 1. So it starts with 7, goes up to 0, and the next state is 1, 1, 1, that is 7. That is how a down counter works. Now let us move to the another topic, that is ripple up and down counter. This is a circuit in which we can define that the sequence will count up or sequence will count down. For this particular purpose, we use another input signal which will decide that if we have to count up or we have to count down. So here we have used u oblique d bar. So whenever its value is 1, it will count up, the 0, 1, 2, 3, 4, 5, 6, 7, then 0. When its value is 0, it will count down 0, 7, 6, 5, 4, 3, 2, 1, 0, and 7, like this. So the design is clear. Here we have used another pin M. M is connected to gate number 2 and gate number 4. M bar is connected to gate number 1 and gate number 3. So whenever M is 1, so whenever M is 1, M bar will be 0. So gate number 1 and 3 will be deactivated. Whenever these are deactivated, QA bar and QB bar will be the clock, that means down counting. Whenever M equals to 1, M equals to 0, then M bar will be 1, then gate number 1 and 2 will 1 and 3 will be activated. Output of 2 and 4 will be 0, because for the AND gate, if any input 0, output is 0. So in that case, QA and QB will act as clock pulse and it will count up. In the same way, you can design, you can draw the timing diagram defining M equals to 0 and M equals to 1. Whenever M equals to 0, it will count up. Whenever M equals to 1, it will count 0, down. Now another situation comes for an n bit counter. It is desired that it will count up to 2 raised to power n states. Now if we have to design a asynchronous counter which counts up to a particular mode, suppose we are using a 3-bit counter and we say that we have to count up to only 4. So here in this case, the mode 4 is the mode. Number of states is the mode, and whenever we have to design a asynchronous counter with mode number less than 2 raised to power n, because for any n bit counter the number of states will be 2 raised to power n. So here we are designing a asynchronous counter which has a number of states which are always less than 2 raised to power n. So how to design this type of circuits? Let us discuss. States may be skipped resulting in a truncated sequence, means we are syncing our sequence. Now technique used, force counter to recycle before going through all the states in the binary sequence. If we can define a logic circuit, whenever if we want that it will count up to 4, so after 4 it will reset the flip-flop. Whenever a state 5 comes, the circuit should be like this. Whenever 5 comes, it should reset the flip-flop and the output of the OR flip-flop should be 0 0 0 like this. Example, given the following circuit, determine the counting sequence and hence the modulus number. Suppose we have a flip-flop, all inputs j equals to k equals to 1, we have put it. A is the LSB, A, B, C, output of A is clocked to the B, output of B is clocked to the A, and here we have put it that j equals to k equals to 1. This is our assumption, and master clock is given to flip-flop A. What have we have done? The C and B are NAND, and it are all connected to the clear input of all the flip-flops. So what happens whenever C is 1 and B goes to 1? So here C is 1 at this moment, it will start from 0 0 0, then 0 0 1, 0 1 0, 0 1 1, 1 0 0, 1 0 1, and whenever both B and C tries to 1, here you can see at the 6 clock cycle, C is 1 and B goes to 1. So whenever B equals to 1, C equals to 1, then the output of the NAND gate will be 0. And this 0 is connected to the clear. So what happens? The all flip-flop will be reset to 0, then the output will be 0 0 0. So you can see that initially it must count up to mode 8. And what happens whenever the input output is 1 1 0, a circuit is cleared and it starts again counting from 0 to 5. So what happens? We can say it is counting from 0 to 5, or overall a total 6 states. State number 7 and 8 are missing. That means we can say that it is a mode 6 counter. So what happens? Mode 6 counter clears the flip-flop after 6 modes, and whenever 7th state, that is 6 occurs, Z110, it will clear all the flip-flops and count will start from the 0. So you can say the same happens again at the 12th state. Whenever output is again 1 1 0, 1, here it is already 1 and it is 1. Whenever both B and C goes to 1, the all flip-flops will be cleared and the output of the flip-flop will be 0 0 0. So this is the way when we have to design a mode n counter. So the counting sequence, it goes from 0 0, the first state is 0 1 2 3 4 5, and whenever the input output is 6, the NAND gate is 0, and whenever NAND gate is 0, the output of the flip-flop will be 0 0 0, and it will start counting again. In the same way, so this is the mode 6 counter. It starts from 0 1 2 3 4 5, and whenever it goes to 6, it will reset to 0. The 7th state, 8th state, which is 1 1 1, is missing. Now this 6th state 1 1 0 is known as the temporary states. It will occur only for a micro or millisecond duration. Now come to the important Ripple BCD counter, that is asynchronous binary coded decimal counter, or we can say the decade counter. So as the BCD, we need 4 bits to represent a BCD number, and it starts from 0 and go up to 9, and after 9 it must be 0, because in case of the BCD 6 states are unused, because due to 4 inputs the total number of states will be 2 to the power 4, that is 16, ranging from 0 to 15, but in case of BCD we require only 10 states 0 to 9. So 6 states in the BCD are unused. In the same way as we have desired, we can say it is a mode 10 counter, mode 10 ripple counter, because we have to count only 10 states. So what happens? The BCD counter or a decade counter are counters with 10 states, that is modulus 10 in their sequence. They are commonly used in daily life, that is utility meters, odometers, like etc. Design an asynchronous decade counter. So here we have used, again, as we have to count only 10 states, that is up to 1001. So whenever 1010 occurs, 10 occurs, it should reset or it should clear. So here comes 1010, that is the 10 1010. So I have taken one A from here and C from here, and I have used a NAND gate. Whenever 1010 occurs, the output of the NAND gate will be 0 and it will clear the flip-flop, and again it will start from 0 to up to 9. So the logic is what we have discussed in the previous slide. The same logic is used here. We have to clear the flip-flop whenever a temporary state occurs in the asynchronous circuit. So here is a circuit diagram along with the timing diagram. So it starts with 0 0 0 like this. Output of the NAND gate is 1 throughout this. So whenever 1010 occurs, so 101, this occurs for the very short duration. So whenever 1010 occurs, the output of the NAND gate will be a clear pulse, that is a negative going edge. And whenever this occurs at the clear input, the output of the all flip-flop will be cleared, and it will again count starting from 0 0 0 0, and it will go up to 1001. So this is the way how a ripple counter works. So in the ripple counter, we have studied about ripple up counter, ripple down counter, ripple up down counter, and a modulus n counter, in which we have discussed mode 6 counter and the decade counter, that is modulus 10 counter. So I think we should stop here, and